1.3.2. Using a graph to determine where a function is increasing, decreasing, or constant. As part of exploring how functions change, we can identify intervals over which the function is changing in specific ways. We say that a function is increasing on an interval if the function values increase as the input values increase within that interval. Similarly, a function is decreasing on an interval if the function values decrease as the input values increase over that interval. The average rate of change of an increasing function is positive, and the average rate of change of a decreasing function is negative. Figure 3 shows examples of increasing and decreasing intervals on a function. Figure 3. X, f of x. Increasing. Decreasing. Increasing. F of b is greater than f of a, where b is greater than a. Increasing. F of b is less than f of a, where b is greater than a. Decreasing. F of b is greater than f of a, where b is greater than a. Increasing. The function f of x equals x cubed minus 12x is increasing on, open parenthesis, negative infinity, negative 2, closed parenthesis, union, open parenthesis, 2, infinity, closed parenthesis, and is decreasing on, open parenthesis, negative 2, 2, closed parenthesis. While some functions are increasing or decreasing over their entire domain, many others are not. A value of the input where a function changes from increasing to decreasing as we go from left to right, that is, as the input variable increases, is called a local maximum. If a function has more than one, we say it has local maxima. Similarly, a value of the input where a function changes from decreasing to increasing as the input variable increases is called a local minimum. The plural form is local minima. Together, local maxima and minima are called local extrema, or local extreme values, of the function. The singular form is extremum. Often, the term local is replaced by the term relative. In this text, we will use the term local. Clearly, a function is neither increasing nor decreasing on an interval where it is constant. A function is also neither increasing nor decreasing at extrema. Note that we have to speak of local extrema, because any given local extremum as defined here is not necessarily the highest maximum or lowest minimum in the function's entire domain. For the function whose graph is shown in Figure 4, the local maximum is 16, and it occurs at x equals negative 2. The local minimum is negative 16, and it occurs at x equals 2. Figure 4. X, f of x. Increasing. Local maximum coordinates are negative 2, 16. Decreasing. Local minimum coordinates are 2, negative 16. Increasing. Local maximum equals 16 occurs at x equals negative 2. Local minimum equals negative 16 occurs at x equals 2. To locate the local maxima and minima from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points, respectively, within an open interval. Like the summit of a roller coaster, the graph of a function is higher at a local maximum than at nearby points on both sides. The graph will also be lower at a local minimum than at neighboring points. Figure 5 illustrates these ideas for a local maximum. Figure 5. X, f of x. Increasing function. B, f of b, is the local maximum. Decreasing function. Figure 5, definition of a local maximum. These observations lead us to a formal definition of local extrema. A. Local minima and local maxima. A function f is an increasing function on an open interval if f of b is greater than f of a for every two input values, a and b, in the interval where b is greater than a. A function f is a decreasing function on an open interval if f of b is less than f of a for every two input values, a and b, in the interval where b is greater than a. A function f has a local maximum at a point b in an open interval, open parenthesis, a, c, closed parenthesis, if f of b is greater than or equal to f of x for every point x, where x does not equal b in the interval. F has a local minimum at a point b in the interval, open parenthesis, a, c, closed parenthesis, if f of b is less than or equal to f of x for every point x, where x does not equal b in the interval. Example 7. Finding increasing and decreasing intervals on a graph. Given the function p of t in figure 6, identify the intervals on which the function appears to be increasing. Figure 6. T, p of t. Solution. We see that the function is not constant on any interval. The function is increasing where it slants upward as we move to the right and decreasing where it slants downward as we move to the right. The function appears to be increasing from t equals 1 to t equals 3 and from t equals 4 on. In interval notation, we would say the function appears to be increasing on the interval, open parenthesis, 1, 3, closed parenthesis, and the interval, open parenthesis, 4, infinity, closed parenthesis. B. Analysis. Notice in this example that we used open intervals, which are intervals that do not include the endpoints, because the function is neither increasing nor decreasing at t equals 1, t equals 3, and t equals 4. These points are the local extrema, 2 minima and a maximum. Example 8. Finding local extrema from a graph. Graph the function f of x equals 2 over x plus x over 3. Then use the graph to estimate the local extrema of the function and to determine the intervals on which the function is increasing. Solution. Using technology, we find that the graph of the function looks like that in figure 7. It appears there is a low point, or local minimum, between x equals 2 and x equals 3, and a mirror image high point, or local maximum, somewhere between x equals -3 and x equals -2. Figure 7. X, f of x. C. Analysis. Most graphing calculators and graphing utilities can estimate the location of maxima and minima. Figure 8 provides screen images from 2 different technologies, showing the estimate for the local maximum and minimum. Figure 8. A. X, y. 2.44948898, 1.63299932. Figure 8. B. Maximum. X equals -2.449491. Y equals -1.632993. Based on these estimates, the function is increasing on the interval, open parenthesis, -infinity, -2.449, closed parenthesis, and, open parenthesis, 2.449, infinity, closed parenthesis. Notice that, while we expect the extrema to be symmetric, the 2 different technologies agree only up to 4 decimals due to the differing approximation algorithms used by each. The exact location of the extrema is at plus or minus square root of 6, but determining this requires calculus. Try it number 4. Graph the function f of x equals x cubed minus 6x squared minus 15x plus 20 to estimate the local extrema of the function. Use these to determine the intervals on which the function is increasing and decreasing. Example 9. Finding local maxima and minima from a graph. For the function f, whose graph is shown in figure 9, find all local maxima and minima. Figure 9. X, y, f. Solution. Observe the graph of f. The graph attains a local maximum at x equals 1, because it is the highest point in an open interval around x equals 1. The local maximum is the y-coordinate at x equals 1, which is 2. The graph attains a local minimum at x equals -1, because it is the lowest point in an open interval around x equals -1. The local minimum is the y-coordinate at x equals -1, which is -2. 1.3.3. Analyzing the toolkit functions for increasing or decreasing intervals. We will now return to our toolkit functions and discuss their graphical behavior in Figure 10, Figure 11, and Figure 12. Figure 10. Function. Increasing, decreasing. Example. 1. Constant function. f of x equals c. Neither increasing nor decreasing. 2. Identity function. f of x equals x. Increasing. 3. Quadratic function. f of x equals x squared. Increasing on, open parenthesis, 0, infinity, closed parenthesis. Decreasing on, open parenthesis, negative infinity, 0, closed parenthesis. Minimum at x equals 0. Figure 11. 4. Cubic function. f of x equals x cubed. Increasing. 5. Reciprocal. f of x equals 1 over x. Decreasing. Open parenthesis, negative infinity, 0, closed parenthesis, union, open parenthesis, 0, infinity, closed parenthesis. 6. Reciprocal squared. f of x equals 1 over x squared. Increasing on, open parenthesis, negative infinity, 0, closed parenthesis, decreasing on, open parenthesis, 0, infinity, closed parenthesis. Figure 12. 7. Cube root. f of x equals cube root of x. Increasing. 8. Square root. f of x equals square root of x. Increasing on, open parenthesis, 0, infinity, closed parenthesis. 9. Absolute value. f of x equals the absolute value of x. Increasing on, open parenthesis, 0, infinity, closed parenthesis, decreasing on, open parenthesis, negative infinity, 0, closed parenthesis. 1.3.4. Use a graph to locate the absolute maximum and absolute minimum. There is a difference between locating the highest and lowest points on a graph in a region around an open interval, locally, and locating the highest and lowest points on the graph for the entire domain. The y-coordinates, which is the output, at the highest and lowest points, are called the absolute maximum and absolute minimum, respectively. To locate absolute maxima and minima from a graph, we need to observe the graph to determine where the graph attains its highest and lowest points on the domain of the function. See Figure 13. Figure 13. X, y, f. Absolute maximum is f of 2, equals 2. Absolute minimum is f of 0, equals -2. Not every function has an absolute maximum or minimum value. The toolkit function, f of x, equals x cubed, is one such function. A. Absolute maxima and minima. The absolute maximum of f at x, equals c is f of c, where f of c is greater than or equal to f of x, for all x in the domain of f. The absolute minimum of f at x, equals d is f of d, where f of d is less than or equal to f of x, for all x in the domain of f. Example 10. Finding absolute maxima and minima from a graph. For the function f shown in Figure 14, find all absolute maxima and minima. Figure 14. X, y, f. Solution. Observe the graph of f. The graph attains an absolute maximum in two locations, x equals -2 and x equals 2, because at these locations, the graph attains its highest point on the domain of the function. The absolute maximum is the y-coordinate at x equals -2 and x equals 2, which is 16. The graph attains an absolute minimum at x equals 3, because it is the lowest point on the domain of the function's graph. The absolute minimum is the y-coordinate at x equals 3, which is negative 10. 1.3.5. Media. Access this online resource for additional instruction and practice with rates of change. Average rate of change. http://openstaxcollege.org/Lazarok closing parenthesis.